All right, we are back with part 3 of the twin primes and proving that there are infinite twin primes and the twin prime conjecture. I took another short break. Excuse me. I know my throat's going to get raspy or dry out. I drank some water and stuff. I don't care, though. I want to kind of crank some of these out and just make some content and grind it because my mind was on a roll. So if you're just seeing this, obviously go back and watch part 1 and part 2. Excuse me. And we are showing how to prove that there are an infinite number of twin primes. And we showed that there are 2 surfaces you can use, that if you pick values that aren't on either surface, they generate a twin prime pair. Then we broke those surfaces down into rows, and we came up with the formulas for lines that represent all the values that are not on the rows of those surfaces, which are the values that we want, the values that are not on the surfaces. Then we just started working with a certain set of those lines. For each row, there are more and more lines that you can choose from, but we just chose the first line for each row to represent that there are the values from those lines represent values that are not on the surfaces on those rows. And then what we did from there is we said, well, can we show that there are an infinite number of those? So we said, well, we can show that there's an infinite number of values that don't appear in the first 2 rows, and then any subsequent 3 or any 2 rows. But then we just said, well, let's start from the first one and do the first 3 rows, and the first 4 rows, and the first 5 rows, and the first 6 rows. And that's where we were up to. And we showed that we can find, a generating function or this kind of integer solutions for an infinite number of values that will not appear. Though we should say there are an infinite number of values that do appear on the first 6 rows, but those values are values that do not appear on those corresponding rows of the surfaces. So I hope that makes sense. So we're looking for values that do appear on our I guess you could think of this other surface we've been working with as a third surface if you want. But we're showing that there are infinite values that do appear in the first n rows of our third surface, which means they don't appear in those same n rows of our first 2 surfaces. And we were getting ready to generalize now what that formula is to show values that don't appear in the nth rows of or that do appear in the nth rows of our third surface, which means they don't appear in the nth rows of our first 2 surfaces. So let's go with that. I think that at least makes it clear for people who watch the first 2 videos and who are following this topic or who have taken the time to look at it a little bit. Okay, so where were we? So to generate the formula for all the rows now, to generalize this, we're going to examine equations 17, 21, 25, and 29. And I have them here again, but I'm just going to scroll back for a minute for edification for those who are watching the other videos. So we're going to look at 17, 21, 25, and 29. So you want 17 was this form here where we found our relation between those rows. 21 was the next pair that we looked at. 24 was that next pair that we looked at. Or 25, I said. And 29. Right here. So, and also 33. Or no, they're listed as equation 33. So, and the one that we just had here, 32, of course. So if you go back and look at those equations, you'll see that the one for row 3 was this, the one from row 4 was this, the one from row 5 was this, the one from row 6 was this, and then I said I also included the next corresponding relation from row 7. So the same way I sped this up here, and I kind of did the process 5 times, but then for the 6th one I just said here are the results. I did it once more, and I didn't even show you the whole thing, and I got the next one for what would be row 7. And you can see that here. Or hold on. I guess that's the one from row 6. Also shows the corresponding relation between row 7. So, okay, between the two rows. But in any case, we're just showing you all the ones that we just did. Oh, I guess because I didn't actually then take that on and set it equal to 15x plus 7. So that's all I meant by that. So here it is, taking that next part as if we had continued on. Okay. So now, is there any way for us to figure out where these values are coming from more easily than going through that whole step and process that we did? Or to really say, what did we pull out here and where did it come from our process? Let's understand what's going on here. Where do the values in these equations emerge from, and what is being compared between the left and right side in each case as we went through this process? The process began with all values of 3x plus 2 on the first row not being on the first rows of those other surfaces. From there, it was determined that the 3x plus 1 values on row 2 were the ones that intersected the first row. Using r equals 2 with x in equation 16 showed that the members mapping in from row 3 to row 2 into those 7, using r equals 2 with x in equation 16 showed the members mapping in from row 3 to row 2 in the 7x plus 3 positions. Okay. So the 3x plus 1 values on row 2 were the ones that intersected the first row, and the showed the mapping from row 3, row 2 into the 7x plus 3 positions. In equation 17, the set was arbitrarily assigned. Oh, okay, yeah, I remember now. This was something I wanted to mention too. So in equation 17, the set was arbitrarily assigned by me into the right side of the relation as 7y plus 3 as to set the precedent going forward of the lesser valued parameters on the left when comparing sets. Now, what do I mean by that? I guess I should go back and talk about that real quick. So let's go back to equation 17 for a second. And what do I kind of mean here? So what I meant by that statement that I just made there was that when we calculated this step, we had this relationship between these two lines, or what we call lines. They're just the values that represented what we were looking for at that part. But I could have called this y. I was just generalizing things, and I could have called this y and this x. And I did it this way because I put the smaller line, if you will, or the smaller slope line on the left and the larger slope line on the right. But that was just a convention that I chose. I could have done it the other way. And that kind of becomes important when you try to generalize what's going on these two sides of these equations that I listed. So I just wanted to make a mention of that's what I meant. If you're reading the paper and you go, what did he mean by that? That's what I was talking about. Where were we? Okay. So that set that precedent going forward of the lesser value parameters on the left when comparing those sets. So these are the sets represented and compared in row 3 of equation 33. So that was me talking about that there, which I just scrolled back to you and showed you in 17. But and they went on to generate the 15y plus 7 set using equation 17 to 20 as seen in the right side of row 4, equation 3. So these sets went on to generate this value over here. And I'm pretty sure I'm going to go on to say that these sets went on to generate this value over here. And these sets went on to generate this value over here. And so forth and so on. But I'm sure I have it explained here, so we'll see in a second. So from that point forward, the left equations, so I mean left equations, I'm talking about this group over here, of the comparisons are from equation 16 for x with r equals little r equals big R minus 1. So what do I mean here? I put this in the words. That is, the left side of the row 4 comparison in equation 33 uses the r equals 3 value with x in 16. The row 5 comparison uses r equals 4. So when I say, you could say, are you going between the 3 and the 4th? And which row are you talking about? Or between the... So in this case, for what I called the row 3 operations, 3x plus 1 and 7y plus 3, or in this case, the row 4 operations, the r that we used in those equations was, the little r was 1 less than that, was r3. And you can see that when you go back in these parts, a lot of times it was like row 5 using row r equals 4. That's what I'm talking about there. So we've got these formulas. Okay, and I guess what am I leading into here? Why is this a little convoluted, or what am I explaining here? Well, I guess we're going to compare these left side and these right sides, and we're going to try to figure out where all these numbers and values came from in a more easy way and generalize it. But what I'm trying to show or to get at here is that you'll notice that from row 4 on here, these values on the left side are pretty easy to see the pattern. 9, 11, 13, 15. These are just the odd numbers again, starting with 9. And these parts just go up by 1. So I don't have to calculate all those forever and ever and go through and learn this pattern. From now, we could see the values that we'd want on our left-hand side, take that form. And the reason it jumps from this 3x plus 1 to this 9x plus 4 on the first one is what I was explaining with, I said, oh, well, we had to use the 3x plus 2 on the first rows, not being on the first rows. It's because that first row is 3x plus 2 that you kind of get like a starting solution, a starting value that dictates what's happening between those first 2 or 3 rows. But once you get past that, the pattern becomes normalized, and you just get this pattern for any row going forward on the left. And that's what we're showing here. So you get 3x plus 1, but then from then on, from row 4 on, all those values, after we figured out our initial starting values that we had to work with from the 3x plus 2, all the values that we get, all these lines on this left side, is what I say here. From that point forward, the left equations of those comparisons are all from equation 16. Every time we were repeating that process of finding the general solution and the specific solutions, we were using our general equation each time, which is why we see that pattern arising. It's the same pattern, just coming from our general equation. But in each case, we were using a little r that was turns out to be this r minus 1. So for row 5, we were using little r4. For row 6, we were using little r5, and so forth and so on, which led to this stuff over here. But that all just comes from equation 16, which is our general form. That is the left side of row 4 comparison in that equation 33. So that's left side. Uses the r equals 3 value, and row 5 uses r equals 4. So that's what I'm just saying, just uses 1 less. So then it's like, okay, well, if we understand where these things came from now, and they just follow this simple pattern all the way down through this process, what about the stuff over here? Can we figure out what's going on with these numbers? And do they normalize, or do they follow? These numbers don't immediately scream like, what's the pattern here? But let's look at it. As for the right sides of those comparisons, the row 4 sets went on to generate the 35-17 set, 35 plus y. So again, and this is what I suspected before, these row 3 sets are what we use to generate the right side of row 4. These row 4 sets are what we use to generate the right side of row 5. These row 5 sets are what we use to generate this right side of row 6. If you go back and see the pattern that we're doing, where these numbers end up coming from, plugging the position functions into the line functions and everything, this is what you're going to find. So the left side all comes from equation 16, and these right sides come from using the 2 values of the previous row. Okay, great. I'm repeating myself here. The row 4 sets went on to generate that set using equations 21 to 24 as seen in row 5 of equation 33. From that point forward, the right equations are generated using the right set from the previous row as the inputs for the sets from equation 16 again. But this time for y, and the row correspondence is r and r minus 2. So from right around here in row 3 and this second value in row 4, from that point on, this left side all just comes from equation 16. And this right side comes from the value, the right side of the value before. However, these parts, the left side of the part of, like, say, row 5, this left side, this part came from a row value of 5 minus 1, which is 4, whereas this part came from an R value of 5 minus 2, which is 3, and so forth and so on, was the R value that we used in part of that calculation to get that next value. So for equation 7, this part came from an R value of 6, a little R value, and this part came from a little R value of 5. And again, that's just becoming familiar with this and going back and looking at what we did and starting to, and I'm going to talk about this more in a second, and recognizing where these values came from. That's what I mean by this section here, though. That is, the right side of the row 6 comparison is generated by inserting the right side of row 5 into the y value in equation 16 with R equals 4, which is 2 less. The right side of the row 7 comparison is generated by inserting the right side of row 6 into the y value in equation 16 with R equals 5, and so forth and so on. So here I'm explaining just recapping and reiterating what we did to get these values. These all come from equation 16, and these all come from taking the previous part and plugging it back in and getting the next row. Because of the R to R plus 1 relation in equation 16, this turns out to be the same as inserting a given right side set into the previous left side for x. For example, 9 times, so what was my example here I gave? Let's see. So this turns out to be the same as inserting a given right side set into the previous left side for x. So let's see if we do that. Here we're looking at 9, 35, and 315. So let me see. Right side of x into the previous left side of x. So yeah. So here we're taking this right side of x, this 35, 17, and we're putting that into the left side of here, 9x plus 4. And here we're taking this 315, 157, and putting in the 11 plus 5. So we're taking the right side of a certain row and plugging it into the left side of the previous row. And that's what I'm saying is you'll notice is what's actually happening here. For example, we take that right side, we plugged it into the previous row, and we got this 315, 157, which was the next one on the right side. So to get each next right side, you take the previous one and plug it into the row from one before that. Okay, so if we know that all these come from equation 16, and now we know how to generate this right side by just taking the previous one and plugging that into this line on the left side of the previous row, we're getting closer to generalizing this, and we can just crank all these out without having to go through the whole process the whole time. And because we have that equation, we can plug it in and generalize it. So that's what we're going to do next. So the left side sets for comparison in row R from row 4 onward are simply, and here's the general form. We said it's the odd number plus the row number. So now I'm using big row R, and we're saying that this is just the odd number plus this. And you'll see it goes up 9, 11, 13, 15, and the y-intercept just goes up 4, 5, 6, 7. Okay, so we found the pattern of that. That's what we're saying here. The left side are simply 2r plus 1 times x plus r. Now we're talking about big row R, which was just our example each time going down by 1. Now for the right side sets and row 5 onward, the slopes m of the sets are the products of the first R3 consecutive odd numbers beginning with the odd number 5. So now what am I talking about here? And I'm going to talk about the y-intercepts in a second, obviously here too. So when you look at what's going on here, you can notice that there is indeed a pattern to these numbers from row 5 on, 35, 315, 34, 65, and so on. The slopes here for this right side. And what are those slopes? Like I just said here, it's the products of the first R minus 3 odd numbers beginning with 5. So for this one, it's row 5. So 5 minus 3, because it's R minus 3 odd numbers. So row 5 minus 3 is the first 2 odd numbers beginning with the odd number 5. So the product of the first two odd numbers beginning with the odd number 5 is 5 times 7 is 35. That's why you see the 35 here. Now for this next row, row 6, it's 6 minus 3. So it's the first 3 odd numbers, 4 odd numbers, so on. But the product of the first 3 odd numbers starting with 5 is 5 times 7 times 9. And you'll see 35 times 9 is indeed 315. So these numbers here, the slope, are just your first n odd numbers, where it's the row minus 3 for n, starting at 5. So you're multiplying products of odd numbers beginning with 5. Row, the number, if we wanted to know row 20, it'd be 20 minus 3 is 17. And we'd multiply the product of the first 17 odd numbers starting with 5. 5 times 7 times 9 times 11 times 13 is 17 of them. And that would be your slope. Okay. Now what about the y-intercept? Can we get a trick for these values out here too? And of course it turns out, well, not of course, but it turns out we can. We have that data. So the y-intercepts are that slope minus 1 divided by 2. So 35 minus 1 is 34, divided by 2 is 17. 314 divided by 2 is 157. And you'll notice that the slope is, or that the y-intercept is 1 less than the slope over 2. Hey, look at that. We've determined that they're from row 5 on. And again, the only reasons that the beginning rows don't follow the pattern is because they were kind of like our initial conditions. And that's just starting with the fact that we had to use 3x plus 2. But because our generating function, our formula 16, was the same after that, and we just followed the same pattern each time, it turns out we do get a pattern for the rest of that system. And it turns out that we can now, instead of having to calculate that all, we have the general formula for that pattern. The left side of our comparison in each row is just going to be an odd number slope plus a number that goes up by 1 for each intercept. And our right side of our comparison is just going to be a number of odd numbers starting at 5 multiplied by each other for the slope, and then minus 1 divided by 2 for the y-intercept. So now we could generate these values for any row. We've got the pattern. Great. Let's write it down generally. So the left set, so for rows are, so the left set for row R, a big row greater than or equal to 4. Here's the pattern I just said, the odd number plus that value of the row number. Right? You can see for 4 it is 4, for 5 it is 5. For row 6, the y-intercept is, for this row 6 comparison as we called it, it's 6, and so forth and so on. So for r greater than or equal to 4, here's your value for your left side. We just generalized it. And the right side set for r greater or equal to 5 is this. And what is all this? Well, that's just what I just described. Here's the product function of the first odd numbers starting at 5 for the row minus 3. So that runs from k equals 2 to r minus 2. That's just those product of odd values that we just showed, times y, plus, here's that product again, minus 1 over 2. So now here's your two generalized forms for these comparisons in each row. So now you have the generalized form for all this, starting from the left side from row 4 and the right side from row 5. Okay. Where do we go from here? Let's see. Where did I go? Let's see. Hold on. And I explained that out loud, but here I'm just talking about 5 times 7 times 9, 5 times 7 times 9, 11. That was me explaining the odd part for the rows, yada, yada. And so here's our two generalized form. The product here can also be expressed this way. So you could turn this product into this form using factorials if you want instead. Okay. So the same way now, for each of these comparisons in our general form now, the same way that we did for each one, we found our integer solutions with S for X and Y. We're going to do that in general now for our general form. So setting equation 34, this is our general left-hand side part equal to our general right-hand side part, has the following integer solutions in equation 37 for row R and an integer S. So now we've found our generating function of our integer solutions for this entire pattern. Here, going all the way down. So you can see it turns out to be that product times S plus the thing minus 1 over 2. For X is going to be that. And Y is just going to be this value, 2R plus 1 times S plus R. So, and then I just gave the same equation again with the factorial packed in. So you could see it either way. So here it is with your product version, and here it is with your factorial version. Great. But what does that show? We've just proven it. This is what we're trying to show. This shows that there's an infinite number of natural solutions in the intersection of any and all rows R. So, and I'm going to get into what I talk about here in a second. But what am I saying here? So what we're saying here is that we found this pattern for any row R. Okay, R can go to infinity, right? But for any R that we choose, for any a million, a billion, up to infinity, for any R that we choose, we can always find we can use this generating function with S here to find values that will not be in all the rows before it. I.e., this is the equation for our infinite set of values which are in no rows. There's no row that you could go to where you couldn't find. So this is basically what this formula shows. That there's no row that you could go to where you couldn't find values that aren't in all of those. Well, again, I have to be careful how I say it. For our third surface, what I call the third surface here, there's no row that you could go to where you couldn't find a value that was in all of those rows. And because it's in all of those rows, it's not in all of those rows on the first two surfaces. So that's what we were trying to show. So, because S is just all integers here, or all natural numbers starting at 0, or whatever. So that's it. There's your proof of infinite twin primes at that point, because there's always no matter what row you go to, there are always some values that will not be on all rows before it. Or again, I keep saying that wrong. How I'm going to say it. No matter, I keep jumping back to the first two surfaces from the third. But no matter what row you go to on that third surface, there will always be some value you could find that is in all rows below it or above it, however you want to think of that on the chart. All rows going down to row 1. And because there's the values that exist that are in every single row of that third surface that we were working with, those values will never be on the first two surfaces. And those values that are not on the first two surfaces always generate twin pairs. So there's an infinite number of twin pairs. And I guess I'm going to continue on what I read there, but I'm going to just go back to the picture for a second, or the rows. Where am I? For the third surface. So this is the third surface. And remember, this third surface was just those first set of lines that we picked. That were the values that were not on those first two surfaces. So, no matter what row you go to in this chart, there's always some value. You've showed that there's always some value in any row that you go to that is always in every single other row above it, or down to row 1. So that's how this proof works, and that's what we're aiming for. Let's see if there's anything else I want to say about this before I go back down to the part we were at. But that's the general idea. You've shown now that, I'm just repeating myself because I'm letting my mind work something over in my head. But you've shown that there's no row that you can go to. Or again, I'm just trying to get better at saying it. Every row that you go to, you can find numbers that are in every row above it. But these are all numbers that are not on the first two charts. And therefore, infinite number of twins. There's no row that you could go to where there would be numbers where you couldn't find some number that wasn't in all these other rows. I think you get what I'm trying to say at this point. So, but it's because of this infinite generating function that's your proof. Right here. This guy or this guy, however you want to think about it. So, okay. Now, I talk about some of the implications of this. It shows that there is an infinite number of natural number solutions in the intersection of any and all rows R. Note, it does not give the specific elements in that set, but simply it proves the existence of the set. And that's an important distinction to make. It shows that there's no row that exists such that an infinite subset cannot be mapped from the first row through the intersection of all subsequent rows to that row. Because these are numbers that are not in range of either of the first two surfaces, there is an infinite number of natural numbers not in the range of those surfaces. Therefore, since all numbers not in the range of those surfaces generate unique twin pairs, there's an infinite number of twin pair primes. Basically, I guess in another way to think about it, we've shown that at some level the density of that surface, or the density of those numbers, that there's an infinite number that are always on that third surface, so not on the first two surfaces. And here's a generating function that can show you which ones will never be on that surface. And I say it does not give the specific elements of the set. And why did I say that? To try to explain it better. Let's see. Again, you have to really become familiar with this stuff to really understand it. But this should get people enough that they can start to work it out on their own and see what's going on here. Or improve upon it, or use some modular stuff to explain it in a better way. But I guess I said here it doesn't show the specific elements in the set because I'm just checking something on time too. Because you can always go to a higher R, and every time you go to a higher R, you might be pulling out more and more of those numbers. But it still shows that no matter how high of an R you go, there's always numbers that you could pull out. And that's what you're trying to show, that set is not empty, basically. And in fact, because you have this generating function, you show that it's also not only is it not empty, you've got an infinite number of them because S goes to infinity here, and here's all your numbers, So let's see, some notes, and then I talk about more of this. If you really break down the nitty gritty and start to find some of the things that are going on with this, you'll notice a few other things, and I talk about it here. Some notes should be included about the nature of these integer solutions. The first note involves the behaviors of equation 35 and 3738. 37 and 38 were just the two versions of the same thing. But 35 is the equation for the right side set of stuff, which was the odd product of the odds bigger than 5 and then minus 1 over 2 of that. So some notes about these. The first note involves this stuff. Gives an infinite set of integer solutions based on the integer s, which is enough for generating infinite sets for a given row R. However, in cases where the slopes in comparison between x and y have a common divisor, and I'm trying to remember this stuff out on the fly, so bear with me for a second. It does not give all integer solutions. This happens every third row. Let me see if I can get my mind in a state of what was going on there. I'm just thinking for a minute. You'll have to give me a second of silence here. Okay, so I'm just trying to get my mind back in the mindset of what I was talking about here. Okay, so there's something when you look at the actual numbers involved from like this part here, when you're looking at all the rows and you look at these numbers, because we're starting with this thing which is all based in modular 3 in a sense, and because you get things like 9 and 15 and things that are multiples of 3, 8 odd numbers then that are multiples of 3 that come up, 9, 15, I guess the next one would be 21, and so forth and so on. When you do some of the math, you can actually simplify by like a factor of 3 and get slightly different numbers than these. But you can leave it in the full number. How do I want to say this? And again, you'd have to go through this process and really familiarize yourself with it to know what I'm talking about here. But I just want to say it anyway for those who would go through it or start to figure this stuff out or look at it and say, oh, why do those numbers end up this way? There's a point where you could simplify, but you just leave the bigger number because it's like you're not worried about the redundancies. And it's easier to just leave the number because then that shows you this nice pattern. Whereas if you simplified it, you'd still be able to do it, but it would be like you'd have to compensate for that every third term and your math would get more complicated. So you end up skipping some of the solutions. Let's see how I set it down here. In cases where the slopes in comparison between x and y have a common divisor, it doesn't give all integer solutions. This will happen every third row. The full integer solutions for those rows simplify to have smaller slopes than the ones that we had in those equations. Yeah, there's a way you can factor something out and simplify it. But then what that has the effect of generating even more members of the sets. So again, this is one of those cases where you're just looking at an infinite subset, but it's still an infinite set. And you've excluded some that you could have had, which was just give you even more answers. So it actually works in the opposite direction to help the problem, saying that there's even more solutions than what that generating function right here, I guess I said 35 and 37. So there's even more solutions than this generates. And you're missing some of them every third row because of a simplification that I didn't do, but it's easier for finding the overall pattern to not do it. That's basically what I'm saying there. So if you get familiar with this enough and you'll start to do the math, you'll see what I'm talking about. If you were to go through, try all the steps, and look for places that you could simplify, you're getting these redundancies. And so there are even more solutions than this provides, but that's okay. We don't care if there's more. We just want to show that there's an infinite amount. However, adjusting to include all of those complicates equation 35, and it's not necessary since it's still using every third solution from those infinite sets for those rows as stated. So yeah, in those rows, when that happens, it's actually skipping every two of the solutions that it could use, but it doesn't matter. We just needed the third one. Same way in our very beginning, we just chose the first, which I'm going to talk about here again in a second, actually. We just chose the first line out of each of the lines that we needed for, every row has an odd number of lines that increases, and we just chose the first one. We could have done this whole process with those other lines too, and I'm going to talk about that. So it's using every third solution from those infinite sets for those rows as stated, which is of course still an infinite subset. It actually means that there's even more elements in the infinite intersection than the ones shown by equation 37, 38. And this is similar to the second note, which I just started alluding to. Remember that this entire process was done using only the first set of values that were not in each row, those lines. Recall from equations 10 and 11 how each row has an increasing number of sets not in that row. While the first row must use 3x plus 2, there are an infinite number of other combinations with different sets from other rows that generate their own infinite intersections. So you could have used, again, I used the 3x plus 2, you have to, but then from every row after that, there's more and more lines that you could choose from. And it's not immediately clear that every combination of lines that you would choose would give an infinite set. You might be able to choose some that are linearly dependent on each other that don't give an infinite set. But you have more and more lines to choose from, and unless you could show, and again, I don't think this is true at this point, unless you could show that every other combination, none of them give infinite sets, and I just got lucky choosing the first line, and those are all the ones that are modularly, linearly independent, you'd still be okay here because we showed that there's an infinite set, but it just goes to show that we did all this just using those first lines, and that there's an infinite number of other combinations of sets that you could use, and then repeat this process and look for other representations of infinite sets. So that's again what I'm getting at is we've used this kind of common denominator process. These generating functions that we get here, 35 and 36 and 37 and 38, they don't generate all twin pairs. They just show that there's an infinite number of them. And that's an important distinction to make. You'd have to go through every combination for all those lines and try to see an even overarching bigger pattern and pull out what the pattern is that generates all of them. Some of them might be generated by intersecting with some of those other original lines and whatever. But while this first row must use 3x, there's an infinite number of other combinations with different sets from other rows that generate their own infinite intersections. Okay. And again, little caveat there. That part I didn't, that statement there are an infinite number of combinations that you could use that generate their own infinite intersections. That part's the little caveat that I should say, star, asterisk. I'm assuming that there's at least one other combination of those lines that would have an infinite subset. And I think there has to be, since this one doesn't generate them all. Otherwise, I got really lucky just choosing the first line of each one. But in any case, lastly, using a given row R for equation 37 or 38, and then generating integer solutions with integers S for all rows less than or equal to R, does significantly increase the chance that the corresponding N will be a twin pair generator, but it does not guarantee it. And what am I saying here, too? So it's kind of like the difference between a finite sum and an infinite sum. we've shown that there's no row R that you could go to where you couldn't find numbers that are in all those rows and thus not in the first two surfaces. However, the function's only good up to each R that you plug in, and there's always a chance that one of those numbers is a number that's in the next row somewhere. Now, it doesn't mean there wouldn't be some other numbers that aren't. Like we said, you just have to go further down and further down. We've shown that there's an infinite number of R, or an infinite number that are in those, that you could, in that whole surface. But for any given R, it doesn't 100% guarantee that all the ones that you would have generated for all the rows before that are going to be twins. There's going to be a few stragglers that aren't, or a few that would be in a higher row, a number that does appear in some other row. And you'd have to, but when you got to that row, you'd rule out all those with that row too. So when you use those functions, like I said here at the end, 37, 38, and you actually go back and you plug in a given R, not just R's infinity, and you generate all the data for all the rows before it and look at all those and which of those intersections and which positions they're in, that kind of thing, you've significantly increased the chance that you will have a twin pair generator. But you're going to get some errors in there because you haven't gone up enough R. But it wouldn't matter if you would. There's still an infinite number of other ones you could pull out. It would just start to take some of the ones out of your set from a lower R, and you'd say, oh, now we're in this ratio of numbers, and here's all the ones that are left. So it does increase the chance that a corresponding n will be a twin pair generator. It does not guarantee it. However, because the set is diagonalized, for any n that is generated for a given R, it's never needed to check for values past row X. And now, what did I mean by this? Again, I haven't looked at this in years, but let's just see if I can get back to it. And what are these cats? Oh, that would be cats knocking stuff off the shelf. Okay. We're okay here. Just checking what they were doing. For any n that is generated for a given R, it's never needed to check for values past row X, where X is the ceiling. So the solution for X, 2x squared plus 2x plus 1 equals n, the equation for the diagonal. Oh, okay. So this goes back to what I was just saying, where because the set is diagonalized, and because the row values increase by the odd number and those slopes get bigger and bigger and bigger and bigger, and because you're only checking up to certain values, the numbers in subsequent rows eventually get so big and they pass any number that you would want to check, in a sense, from any previous rows. So you don't have to check the whole chart. So, okay, so why that again, this has to do with the limit of row R that you're on and how that affects that generator. So yeah, that's what I'm talking about here. The corresponding. So yeah, using that generator to generate all the data for any row less than or equal to R significantly increases the chance that you'll have the number that would generate a twin prime. It doesn't guarantee it, but then you'd say, because that number could appear in a further row, but it can't appear in a row like super far ahead. There's only a number of rows before that row starts past the number that you would be checking. The first value in the row is greater than the number that you would be looking for in that row. So therefore that number will never appear in that row. That's what I'm trying to say. And that happens, and here's where that happens at. Or another way to say this is using that function to generate values to look for twins, and then you get all your values up to a certain point, But then you take the largest one of those values and you check a few more rows up to using this formula here, and then you would know that at least all the values that you would calculated less than that value will generate twins for you. That's kind of another way to say it. So again, you'd have to really become familiar with this system and know the ins and outs of it yourself. But I put that in there because that was something I noticed at the time and wanted to talk about and be complete and say, okay, this is what's going on in this situation. So, in conclusion, the proof used the fact that all prime numbers greater than 2 are odd, that are not odd composites. That's how we started. It generated the two surfaces from that requirement, one for each member of the twin pair. We had the lower prime surface and the upper prime surface, prime 1 and prime 2 surface. It shows that numbers not in the range of either surface always generate the twin pair. We showed that at the very beginning. Any numbers that are not on either of those surfaces, when you do 2n plus 1 times that generator, will be the first number of a twin prime pair. So all you have to do is show that there's an infinite number of numbers that are not on the range of each of those two original surfaces. And that's what we did. We wrote down a third surface, basically built out of all the lines. We found lines that represent numbers that are on neither row of those surfaces. We chose the first line. We made a third surface that says, hey, all these numbers will not be on either of those first two surfaces. Can we find an infinite number of these? And numbers that are in every row of our new third surface or aren't, there's an infinite number of those. So that density of that set is not 0. It contains an infinite number of elements according to this. That's basically what we showed. We showed that that set contains an infinite number of elements. And it mostly gives you those elements themselves specifically too. Not only does it show that there's an infinite, you can use it to calculate most of them or go back, but you have to do some double checking and go further than you want to check to generate all the numbers less than a certain number because you're just going R to infinity, that kind of thing. So, I hope you enjoyed this. This has been about 3 hours now. This is the third hour. We're at like 50 something minutes, 53 minutes. And so, again, I think if this is the general technique, could somebody improve it or maybe come up with a cleaner way than all that row arithmetic and finding the general pattern? Maybe. If they just see those general lines that I started with, the 3x plus 2, the 5x plus 3, 7x plus 4, so forth and so on, somebody might be able to look at that real quick and come up with a modular proof and just say, oh, yep, here you go. These are the values. Or look, here's an infinite set that's going to be in all these, and so therefore it's not on the first surface. I think there's much easier ways to show it. I just didn't know how. And this was the best way that I could show that there was an infinite set of values that never appear. And once you do that, you've proven the twins. That's all you got to do to prove the twins, is from that very interesting starting premise with those two surfaces, show there's an infinite number of values not on either of those surfaces, and you've proven the twin prime conjecture. And so now that I've made this might be enough. There's a whole other proof in this paper because I had an original proof. I guess I'll talk about that real quick here since I've got another 3 or 5 minutes if I want to keep it under an hour. If I talked about the second one, it's basically a bunch of different math that leads a different technique, but it ends up with something very similar in the end. And it was that same thing that was similar in the end, which I didn't actually prove in my first paper explicitly enough. I didn't feel like it was rigorous enough. And it made me think of how to do all this. And I came up with this method, which I think is much better. So I don't know if I'll make the second video. I don't think at first or for a while too many people are going to watch this. They might. There's not too many people who really get into this stuff. There is enough. There are definitely people who do, but this is a very heavy video and you really got to take the time to break down all these topics. But let me really briefly gloss over what's happening in the second paper. And maybe eventually, or if somebody wants, I'll make a whole video on that. You can get this paper and read it and look at it. So the first paper technique we just talked about was the surfaces. Two surfaces and, odd composites and all that. And you make the surfaces and generating numbers and great. So this is similar. Let me just look here real quick. So I don't remember if I used the exact two same surfaces, the ones I got from 2ab plus 1 times, or 2a plus 1 times 2b plus 1, that whole thing at the very beginning of this. I think I used different surfaces. I'd have to go back and reread it and double check. But the idea, again, is to show that there's an infinite number of values that don't appear on that surface, an infinite number of holes somewhere on that surface, and thus there's an infinite number of twins. But I go about it a completely different way, and I think with two different surfaces. I want to finish this up, so I'm just going to skim and scan this really quick and explain some of what's going on really, really briefly. Not get into all these parameters. So in this case, the values end up being things on a parabola, and I had to try to parse those values a certain way. And I realized you could take this line and start passing it over the parabola. And by passing it, I mean kind of moving the y-intercept so that the thing slides over. And you're looking for positions where the line hits the parabola on integer values. Like here, this one would be here, and this one would be here. And this is diagonalized too. But it's a technique that starts to go about that. And the surface values are mapped to these parabolas. You scan across them, and then you start to say something about these lines scanning across these parabolas. And you end up adding a second line. And then how do you compare the two? And we're trapping a certain value is what we end up doing. And where I can say it this way too, and at least in words real quick to give you a premise of what the second proof is doing. In the first proof, we looked for the infinite holes between all the lines that represented the values on these two surfaces that we generated. And we're looking for infinite values there. On this one, I didn't see it in terms of lines and infinite values. I had the same kind of charts and surfaces, and the chart's diagonalized. And there was literally one position in the chart that I recognized the value never appears at the diagonal. Like, this is doing a really quick job here of it, but the values of the diagonals -1. And if you go down the diagonal and you subtract 1 from those values, it was a position where that number would never show up. So it was like this one hole based off of things that were one away from a diagonal. And then I start talking about that hole, and you have to show that there's an infinite number of those, and that's what this does. So it's a similar idea, but a slightly different construction. And those hole values end up being on the parabolas, and then you use the lines to scan them. And I'm going through here, and this is just an example of lines moving across. That's why you see 3 lines. Oh, it's a second parabola. It's not a second line. The lines are like the scanning, but it was a second parabola. And you squeeze the value between the parabolas using the lines. And the main point of this is I want to get to the end and make a comment about what led to the proof that you did see. So this is it, and I might make a video on this, but same idea. You're going through, you're squeezing these parabolas. Here's like similar charts just showing, like here you can see the diagonal 1, 4, 9, 16, 25, and it was based off of the squares. And it was like something where you get to the square on the second chart here, these are shifted a certain way, and then it's like certain values -1 at a certain rows and columns over never appears, and you start talking about that. But it ends up resulting in something that almost comes down to like the first proof, where you have to go through something similar to the whole first proof anyway. And I kind of gloss over at the end, and I wasn't happy with that. So finding these non-occurring values. See, here we're doing something similar, and it goes through the whole logic of what you're doing, diagonalize. I saw that word, diagonalization, squares. Like it's I kind of remember, again, this has been 12 or 15 years on this one or something. And of course, if I reread it, I could refamiliarize myself, but to just do it here off the fly. But here it's defining these parabolas. You start to get down to this parabola. Let's see, hold on. Shrinks to only two values. So you get these two, it ends up getting these two parabolas, and you're looking for integer values that appear like right here between the peaks of the two parabolas. And it's a technique that does something like this. So here you're using this other one and you're scanning and you're combining this all to get this value in between. So I remembered that was going to come up. And then filtering and the generating parabola. So you end up getting this condition that x can't equal this square root thing here. So similar to before, you get certain values that x can or can't be. And then you also get this position here that x equals, x can't be this. And here's the end of the crux. So I say, therefore, since there are an infinite number of odd numbers with no natural solutions to this and this, then there's infinite generating values. So in this one, it was solutions that weren't this and this were generating values or something. And I just kind of say this. I say this, since there's an infinite number of odd numbers with no solutions to this and this. And here's me recapping and talking about it. At this point, the proof concluded in a bit of a hurry, and one might notice a few things about the last sections. What happened to worrying about specific columns, something I was talking about in this. But I never, even though this was kind of obvious to me at the time, I never really proved that part rigorously or something, and it didn't, and I wasn't happy with it. And it basically amounts to like proving that there's an infinite number of values not on two other surfaces, and here's two other surfaces that you end up being able to use under these square roots. And then I just talk about that here. So there is another way to go about it and kind of isolate values that show there's an infinite number. And if I remember right, I think I found, like in my original proof, without all the rows and lines and crazy arithmetic that the other one used, it's actually more clear in this proof, like the values that don't show up in this one little pocket I found and why all those values generate infinite number of primes. However, you're tasked with this thing at the end, which just ends up being like the first proof anyway. This thing with these numbers with the square roots, where it was just like proving that there's this condition right here. But basically, I'm going to end on that and just recap that this second proof. So this whole second proof ends up showing this condition, that this is another condition that you can show is equivalent to proving the twin primes. That if you could prove that there's an infinite number of odd numbers with no natural solutions to this here, then there's infinite twins. But I kind of just, at that point, I did the whole, it's just left to an exercise to a reader, or this is obvious. And I didn't actually do it in the first one, and that wasn't good enough, which is what led to the whole more rigorous, analytical thing of the second proof, which is the one I actually have first in this paper, which you saw. But, yeah. So let's see. But yeah, so basically what you're looking at here is an equivalence to the twin prime. Through this whole second paper, you could generate this as your equivalence. If you can show that there are an infinite number of odd numbers such that there's no n and m that can generate it with this function or this function. So an odd number that can't be generated by this or this. And if you can show there's an infinite number of those, you can show infinite twins. So that's what this whole paper distilled down to, into these two square root functions here. And you have to show that there's an infinite number of odd numbers that cannot be made from this form or this form. And at the time I originally came up with it, I think I felt it was so evident just from like under the radical with this form and the n plus 1 and the 1 plus 9 versus these things here or something. I thought it was just like obvious, and I didn't actually do that part. It was like, what? You can't do that. You gotta complete the whole thing and show every little step. And so, but yeah, this part's left for an exercise to the reader. So it's obvious here, right, that you can't have there's an infinite number of odd numbers that can't be made from this or this. So yeah, but this is another equivalence to the twin prime here. And that's what this other second paper with the parabolas and lines the logic ends up generating this as your condition. So I'll leave it at that. If anyone has any questions or wants to reach out or talk about this stuff, again, this is some very heady stuff for people who are just into prime number nerds and math nerds who really like this kind of thing. But feel free to ask questions, and I hope you enjoyed. I hope you enjoyed this proof on the twin primes and why there's an infinite number of twins. All right, thanks for watching. Have a great one. Bye.